Hello students, today I am going to explain you about the design of liquid storage tanks. Here we are going to study the design using IS code method. For this design we are going to use IS 3370 part 4. So here it is IS 3370 part 4 1967. It is code of practice for concrete structures for the storage of liquids. So what we have already studied in the design of liquid storage tank for the, or let's say it may be circular type or it may be rectangular type, we have studied that with the approximate method. So today we will learn this method using IS code method. So before that, let's briefly learn about the IS code, what we are going to study and how to use this code. This IS code is having part 1, part 2, part 3 and part 4. In the part 1, it is related to theory, means how to construct, what are the types of joints, how to construct the joints. And in part 2, we have the values for the stress, maybe direct tension, bending stresses with the concrete, or it is with respect to the steel. We have the values that are to be used in the design. And this part 4 gives us design tables. You may see, I mentioned here that the highest standard code of practice for concrete structures for the storage of liquids, part 4. So here they have mentioned as design tables. So this codebook contains design tables which are going to which will be used by the designers for various constraints, like whether it is a circular one, whether it is rectangular. Again, in the circular or maybe rectangular, what is the type of joint, whether it is hinged, whether it is fixed, and if the tank is open to atmosphere or it is in again having the top slab, whether it is fixed or hinged. So such conditions are there. Again, at the bottom slab, whether the slab is being hinged or whether it is fixed to the walls. So that is another constraint here. So with respect to this, we have many tables, and these tables are having the coefficients, moment coefficients and shear force coefficients. So let us study in brief about the rectangular tanks and what are the coefficients that are being given and how to use these values. So this codebook is having, or this part deals with the design tables as it is mentioned in the codebook itself for rectangular and cylindrical concrete structures for the storage of liquids, means rectangular and circular water tanks or liquid storage structures. The other part of this code are, the what it contains here is part 1 general requirements, part 2 reinforced concrete structures, as I said, part 3 it is related to the pre-stressed concrete structures, and this particularly part 4 is having the design tables. In this particular part, It starts with rectangular tanks. So this standard part 4 comments the design tables which are intended as an aid for the design of the reinforced or pre-stressed concrete structures for the storage of liquids. Rectangular tanks. Moment coefficients for individual wall panels. Moment coefficient for individual panels considered fixed along vertical edges means surrounding walls are being restrained or they are fixed to each other. These vertical edges are fixed but having the different edge conditions at top and bottom. So these are being given in table 1 to 3. Means first 3 tables are having these. First one, that is table number 1, is having top hinged and bottom hinged. Second table, top free and bottom hinged. And third table is having top free and bottom fixed. These are the 3 different conditions. So all these 3 conditions are with respect to the walls are fixed. These are the vertical edges are being fixed to each other. That is a one common condition here, and along with this, these are the 3 conditions with the 3 tables. So conditions in the table 3 are applicable to the cases in which wall slab, counterfort and base slabs are built integrally. Means bottom slab is fixed, means walls and the slab are being constructed monolithically. They are being built integrally. And moment coefficient for the uniform load on rectangular plates hinged at all 4 sides are being given in table 4. Means here first 3 tables are giving the coefficients for the pressure, water pressure, that is triangular water pressure, but this 4th table is having uniform pressure or uniform loading condition. So that's how they have mentioned here, that for the uniform load. And this table may be found useful in designing cover slab and bottom slab for rectangular tanks with one cell, means one single element. So similarly, we have coefficient for the rectangular tanks, the coefficients for the individual panels with fixed side edges apply without modification to the continuous walls, provided there is no rotation about the vertical edges, means they are fixed. So this is one condition over here. So similarly, we have different tables for different conditions. We will see them. So table 5, 6. So moment coefficient computed in the manner described are tabulated in table 5, 6 for the top and bottom edge conditions as shown for single cell tanks with large number of ratio of B by A and C by A, and here B being larger and C being smaller horizontal tank dimensions. Means we usually consider these B and C as length and breadth of the tank. They are the horizontal dimensions. And what is A? Here in IS code they are using the height as the A. Right, clear? So B and C are the length and width or length and breadth of the tank, and A is the height of the tank. Right? So we have table 1 to 6 for this, and later on the tables are been given for the shear coefficients. So we have figure 1 and figure 2 also for the shear coefficients. Along with this, we have table 7 and table 8 for the shear coefficient to obtain the shear values. And after this table 8, we have a set of tables again where we can obtain the coefficients for the circular tanks. So we'll see them later. So let us see this table 1, figure 1, that is shear coefficient calculation to obtain the shear coefficients. So here the condition is top hinged and bottom hinged. So we have the ratio of depth below the top. So here sides are fixed, that is a condition. So in all cases here sides are fixed, but top is hinged and bottom also hinged, and B by A ratios are being given here. So first one is half, second is 1, third line is double 2, right? B is width, that is length. They have mentioned here again. A is the height of the wall, B is the width or let's say length of the wall, and W here is the unit weight of the or density of the liquid causing the hydrostatic pressure. So this is figure 1. So similarly we have figure 2 also, where top is free, it is not hinged. In the first condition it is hinged, in the second case it is free. Here it is fixed, sides are fixed, and bottom is again hinged. So everything remaining is same here. So shear per unit length is equal to coefficient into W into A square. A means H, height square, unit weight or density of water into H square into coefficient. So these coefficients will be obtained from this figure. So that is one thing, or else we can use the table 7 and 8 to obtain the shear coefficient, and that coefficient into density into H square will give us shear per unit length, right? So this is a small introduction about this code book. So we'll see now. Okay, after this, as I said, table 7 and 8 will be for the this shear values, shear coefficients, and after that we are having the coefficient tables for moments and shear forces for cylindrical tanks, that is circular tanks. So here we have the shape of the deflected shape of the tank. So here the hydrostatic water pressure. So this is the deflected shape. For wall with fixed base, it is fixed here, and free top subjected to the triangular load. This is the triangular load and it is free edge, and here it is fixed at the bottom. And here wall with hinged base, here hinged, and free at the top subjected to the triangular load. So here it is fixed in the first condition, but here it is hinged and top is again free. So next figure is wall with hinged base, free at the top subjected to the trapezoidal loading. Means it is not triangular, it is trapezoidal loading. So this much portion of this WH is the hydrostatic pressure, and this is the uniformly distributed load, or it is uniform load. So uniform load plus this triangular hydrostatic pressure. So in this case we are going to calculate T tension. It is X equal to X, it is T equal to X into VR by H. So where this V is equal to HT by Rx and X is equal to H square by dt. So we will be getting the coefficients with respect to the X value, that is H square by dt. So another case here is wall with shear applied at the top. Means we have the slab above this top portion will be having the slab again. So that is a condition here. So we have different conditions here with a different type of tanks. So we have the movements in the circular slab. So this is the first table what we are going to use for the rectangular tank design. So first table is having movement coefficient for individual wall panels. Top and bottom are hinged and vertical edges are fixed. So here you can observe here, right? So here it is hinged, means there is no hash. These lines, inclined lines, means it is hinged here, and sides here as well as here, these two sides are fixed, right? Then as well as at the bottom again it is hinged, and it is having the triangular shaped hydrostatic pressure, water pressure. So here A, this is the A here, height of the wall, B, that is the length of the water tank, and W is the density of the liquid. So we have two moments here. So one is the horizontal moment and another is the vertical moment. So horizontal moment is my into W into h square. Here it is, sorry, h cube. Here it is A, so it is h cube, A cube. Vertical moment is similar to that, where we will use mx. So horizontal moment will be my into W into A cube, and vertical moment will be mx into W into A cube. Only the change in moment coefficient, my and mx. So we have these values, ratios, that is B by A, that is L by H, and then this is here, this is X by A, means the different locations where we need to obtain the coefficients, and Y is the distance, horizontal distance, that is length for various distance of Y. So Y equal to 0 means, here you can observe here. So this is the axis Y, and from this A value, so Y equal to 0 means it is exactly at the top, means no pressure, 0 at the top, it is 0, and let's say at the half distance means it is A by 2, or okay, we are measuring from this place, right? Okay, small mistake. From here to here we are going to measure. So here it is B by 2 and this side it is B by 2, and if I calculate half of this, again it is B by 4. So exactly at the center it is Y equal to 0, right? And similarly it is x-axis, so x is 0 here, at this particular place it is half, that is A by 2, and here up to it is x equal to A. So x by A means at various values of this. So 1 by 4, half, 3 by 4, and 0. So these values with respect to which we are going to obtain the value of mx and my for the of y equal to 0 or maybe b by 4 2. So b by a is the first one what we need to calculate, that is length by height, and for that particular, let's say L by h is equal to 2. For this we are going to obtain maximum value of coefficient. So maximum value here is this mx, it is 0.42, and again it is 0.28. Okay, this is the positive value at the center span, means at the edges here it is having the positive moment of 0.42, and now we will check for the negative moment, right? So negative moment is at the edges, positive moment is at the center, here it is, right? mx horizontal, mx is vertical moment and my is the horizontal moment calculation. So here we have maximum value of 0.059. We can observe this, right? So we need mainly this value 0.059 and positive value of 0.042. And if we want at the edges here at this place, or let's say at this place, because it is hinged, so we can obtain that. So that values here it is 0.029. If you want to get the positive moment mx at this particular place, or it is again 0.041, and negative value is also available at 3 by 4 value, it is 0.053. So thus we will obtain the coefficients, and that coefficient will be put here, and we know the density and height, so we can get the horizontal and vertical moments. So to know more about this, we will solve the problem, one design problem later. So let's see another table here. So table 2, it is moment coefficient for individual wall panels, top free, bottom hinged, vertical edges are fixed. So only the difference here is bottom is hinged as the earlier case, but top is free. That is the difference. And third table, we can see here, it is top free, sides are fixed, and bottom is also fixed. That is the difference. Remaining it is same. And next, what we have is third one, table 3, movement coefficient for individual walls panels for top, free, bottom and vertical edges fixed. This is the same one, it is continued here. Same thing, it is continued here. So these are the three tables for individual panel movement coefficients. Whatever we have studied now, it is for the individual panel movement coefficient, to obtain the individual panel coefficients. Next one is movement coefficient for uniform distributed load. As I said, it will not be having the this triangular portion water pressure. It is a uniform load here. It is the fourth table, rectangular plate hinged at four sides, means these sides, top, bottom, and these four sides will be hinged. It is related to the table 4. And table 5, it is movement coefficient for tanks with wall free at top and hinged at the bottom. So now it is another case, it is different, where the first these three tables are with the vertical edges fixed and different conditions for top and bottom, and they are for the individual panel. And fourth table is with respect to the uniform load, and this fifth table is having different things. So what is difference here? We'll see. So it is not for the individual panels. Here it is for the walls. They have mentioned that movement coefficient for tanks with walls fixed at top and hinged at the bottom. So it is fixed at the, okay, not fixed, it is free at top and it is hinged at the bottom. That is a condition. And same thing, there is no much difference here. So again it is B by A, X by A is there. And again for the value of B by A, whether it is 3 to 2.5, for the different values we have these tables. So we'll see this. So this is table for B by A equal to 3. C by A, C means it is width, right? B means the length. So for the different length to height ratio, we have the parameters of this B by A. B by H means width to height. So this is for the 2.5 value B by A. That is for our case, our calculation, it will be length by height. L by H equal to 2.5. So we have again continued 2.5 for the different values of this. So it starts with 3. Okay, it is, you can see here 2.5 now. Okay, it is 3. Okay, so it is starting here with 2.5 and up to 0.5. So now it is B by A equal to 2. Again it starts with 2, 1.75, 1.5, 1.25 and 1.75, 0.5. So minimum is 0.5. So next case is B by A equal to 1.5, means length to height ratio is 1.5. So it starts with 1.5 till 0.5. Then again change 1. B by A equal to 1, so it starts with 1, 0.75 and 0.5. So it's whatever is the value of B by A, so it is, you will start with the C by A also, that is L by H, and this minimum maximum value of this width to A, that is also same here. Width to height, that is also same here, and minimum is 0.5. So next condition here is movement coefficient for tanks with wall hinged at top and bottom. So first one was free at the top and bottom it is hinged, but second condition, top as well as bottom are hinged, sides are fixed. So again same thing here for 3, B by A equal to 3, B by A equal to 2.5, starts with 2.5 till 0.5, B by A equal to 2, again it starts with 2 to 0.5, right? And B by A equal to 1.5, 2.5. So B by A equal to 1. So this is the table. So again we have next condition, as we studied. So table number this 5 and 6 for the complete wall panel. It is not for the individual. And next, table number 7 and 8, we are going to study shear coefficients. We will get the shear coefficients here. So again, we have the conditions like hinged, fixed, or free at the top and hinged at the bottom, same thing. And we will be getting the coefficients with respect to the place where we want. So here it is B by A, means it is length to height ratio of different values. So here it is 1.5 means half, 1, 2, 5, 10 and infinity. So these are the values. And what is the condition? Midpoint of the bottom edge, corner at the bottom edge, midpoint of fixed side edge. So these are the different conditions. So with respect to that, we will obtain the values. So this is the second case. Top it is free, sides fixed, and bottom it is hinged. So first case is top hinged and bottom hinged. Sides are fixed. No matter here, there is no difference with the edges. They are fixed. But top here it is hinged and bottom also hinged. But in the second case, top is free and bottom is hinged. So that is the second condition. So table number 7 and 8 are with the shear coefficients. Right? Now, from the table number 9, we will study the tension coefficients with respect to the circular ring wall. Means it is for the circular water tanks. From table number 9, we are going to study with respect to the circular water tank design. So here tension we are going to calculate. It is tension T is equal to coefficient into W into H into R, kg per meter. So we'll see this later on. So now we are going to concentrate only on the this rectangular water tanks. So students, please go through this IS code. Try to study how to calculate the coefficients, obtain the coefficients, and later on we will go for design of a rectangular tanks. So this is a brief introduction to this IS 3370 part 4 1967 for design of liquid retaining tanks using IS code method. So what we have studied here is about the obtaining the coefficients for the rectangular tanks and the circular tanks for movements and shear forces. Right? So go through this once again. Thank you.